for mass on an incline, got a mass here, and gravity pulls it in the vertical direction. To analyze the forces, we construct an x-axis parallel to the incline, a y-axis perpendicular to the incline, and we replace the gravitational force vector with its components in the x and the y directions. So we have projection line here, projection line here. And we do this. Now we replace this force by these two, and then we proceed to resolve the forces. If there's no other force acting except perhaps along the incline, we conclude there's a normal force exerted by the incline equal and opposite to the y component of the gravity. And there has to be a normal force here unless there's some other force parallel to the incline, assuming the incline is strong enough, because the mass is constrained to move parallel to the incline, meaning that there's no acceleration perpendicular to the incline. So these forces have to be equal and opposite. So here's a more extensive labeled diagram. If the angle of the incline is alpha, then the components are, well, the weight is your vector mg, where g is a vector in the vertical direction. Okay, we say that, okay, well, the angle of the incline with horizontal is alpha, but we want to deal with the components of the vector in a circular model. It's just simpler. You don't have to keep worrying about whether you have positives and negatives. So we let theta be the angle from the positive x-axis around to the vector. And in that case, the y component, which I'll call w sub y, is mg sine theta times j. You don't have to make this negative. Theta goes around here. The sine of this theta is negative, and it's going to be automatically negative. And you have wx here equals mg cosine theta times I. Now, the way I'll call the mg vector I'll use an mg vector for the weight, and this is the y component, and this is what I then call mg x. And I put the arrow over the whole mg because I want to regard mg as a vector now, as the weight vector. So there's a little inconsistency in my notation, but it's easy enough to resolve. Okay, so and when I do this, I cross out the acceleration vector, the original weight vector, to indicate that it's been replaced by the two components. So now, this is my weight vector. Now, y equilibrium, as I said, implies that there has to be another force in the y direction. If there's equilibrium in this direction, this can't be the only force. There has to be an equal and opposite force, or some combination of forces equal and opposite to this. Okay, well, in this case, in the case where there's no other force in the y direction, it's got to be the normal force. And that's the response of the incline to mgy, either a compressive response, a response to the fact that the mass is compressing the incline or the material of the incline in the vicinity of the mass, or an elastic response. The incline bends a little bit and releases. And we can see that the force is perpendicular to the incline. I can just take this ball, I don't know where it's going to end up, but I can take this ball and pull down on the incline and release it. Well, that didn't work too well. I need a meter stick. And I've got one here. And the ball tends to, well, okay, I'm going to use a bottle cap. Okay. Okay, so here we go. I release it, and there it goes. It went off this way, perpendicular to the incline, showing how your normal force tends to be perpendicular to the incline. Okay. We can then set up an equation that indicates the equilibrium of the y forces. Normal force plus your mgy force has to equal the zero vector. Has to add up to nothing, to zero. But of course, these are two vectors, they add up to the zero vector. And then we conclude that the normal vector is equal and opposite to the y component of the weight. Now, if there happens to be friction, then we can calculate the magnitude of the frictional force. And actually, okay, if there's friction and the object is moving along the incline, then we have this. Okay. If the object is stationary on the incline, then the steeper the incline, the greater the friction. If the incline gets too steep, friction's going to get broken, and we're going to go to moving friction. Now, I want to be a little more specific. I'm going to put a K on this mu. That's kinetic friction. Okay? So if the object is moving, we have this, and we have net force equals mgx plus the force of friction. And the force of friction, of course, is in the direction that opposes motion. Make a note of that. We discussed it. I didn't put it in the, I didn't write it down on the board. In the direction opposing the motion. Make that arrow point a little better to frictional force. Okay. Now, if a ball rolls up then down an incline, like so, it can be challenging if we don't use the right equipment, or if we try to determine any difference in the acceleration of the ball going up and down the incline. Is the acceleration going up greater or less than the acceleration going down? Depending what instrumentation we choose to use, this can be a very challenging experiment. I roll the ball up, and then it rolls back down. Various problems occur. First place, how do I time it going up? How do I time it going down? it's difficult to get the time when the ball stops, so you don't know exactly when that time is. And also, we want to time it from the instant I release the ball. Now, I could start at some sort of electromagnetic pulse, but of course, this thing is not itself a magnet with a north and south pole until well, I don't want to get into that. Just the only way I can get this thing moving with a magnetic pulse is to have it attracted to the magnet. And if I want to attract it to a magnet up the incline, the magnet's going to kind of be in the way. I get around that, put coils around the entire apparatus and so forth, but that has its own complications. So it can be difficult to time it, but we can use a photogate. Actually, we would need at least 3 photogates. One here, one here, one here. The photogate would detect the position of the ball. As the ball passes, it interrupts a beam between here and here, and there's a signal that goes to a device that will record the signal. That can be a little hard to set up if we want really accurate results, because if the photogate is a little high or a little low, it's going to hit a different part of the ball. We want to set it up so the beam is interrupted right at the center of the ball, right on a plane through the center of the ball and parallel to the incline. Actually, now any plane through the center of the ball would work. Let's not worry about that. Okay, with 3 photogates, we can determine the acceleration of the ball, okay, because that gives us 3 data points. If we know where the photogates are, presumably we do, we have a time and a position here, a time and a position here, a time and a position here. That gives us basically 3 data points. You could visualize that as 3 points on a position versus time graph. And if we know a little bit of pre-calculus, we know that we can perfectly fit 3 data points with a quadratic function. We also know that if we integrate the acceleration twice, we have the position function, and that's, if the acceleration is constant, the position function is going to be quadratic. So by observing 3 points, we can determine the acceleration. And of course, once we get this thing started, we get 3 points going up, 3 points coming down. As long as we get it started fast enough to go through the 3 photogates. And if we don't, we can repeat the trial until we do. So we can determine the acceleration up and the acceleration down. Why do we want to do that? The incline is the same. These forces are the same. Why would we want to do this? Well, it's because there's rolling friction. Without going into all the detail about rolling friction, you have the static friction between the point of the ball in contact with the incline, which is what causes the ball then to roll without slipping. And then you have the rolling friction, which is an energy, it's a source of energy loss. And the sources of rolling friction are a little bit subtle. I'm not going to discuss those, especially at this point of the course. But it's a very low friction between a steel ball and a steel incline, very little friction. So we want to determine if there's a difference, if there's a measurable difference in the acceleration up and the acceleration down. If there is, and the only forces are the gravitational force and the frictional force, the rolling friction, then do we expect that there's going to be a difference in the acceleration? Well, yeah, because friction, if you're going up the incline, friction acts in this direction. If you're going down the incline, friction acts in this direction. Now, we had some discussion about where the acceleration would be greater, and intuition doesn't do much good until you have an intuition about how forces act. But here's the situation. If the ball rolls up, then down the incline, when it's going down, the x component of your force, which is going to be responsible for the acceleration. And let's back up. Of course, the acceleration, by Newton's second law, is directly proportional to the force, assuming your mass remains constant, which it does in this case. Okay, so we just look at the forces. We have the force of gravitational component down the incline, that's this one, and friction opposes it. Well, that means the magnitude of the net force is going to be less than the magnitude of either of these vectors. So your net force is going to be shorter than either one of these, meaning your acceleration is going to be less than the acceleration you would get from either of these. Okay? If you're going up the incline, then the component of the gravitational force parallel to the incline, along the incline, is in the same direction as the friction, because you're moving this way, but friction is, so the friction is pushing this way in the same direction as your gravitational component, meaning that you have a net force vector that's longer. You have a greater net force whose magnitude is greater than either of these forces, so that your acceleration is greatest in this case. If you're moving up the incline, you have the acceleration has a greater magnitude. And that's a little counterintuitive because it's very easy to confuse the velocity with the forces. Not worrying about the velocity vector except for the direction. We get the direction of the friction from that. But then just worrying about the way the forces articulate, this is what we end up with. Okay, well, that's one discussion. Another discussion, and this came up from problems that I posed that people had questions on. I think one of the questions said, explain why the gravitational force on a satellite exerts no torque on the satellite. Well, we, in our discussion, this revealed a pretty imperfect grasp of Newton's law of universal gravitation. Hadn't totally processed the statements, solving problems using the formula without thinking of what the formula means, or thinking about the full statement, which addresses the directions of the forces and so forth. Okay, so you got a planet here, a satellite here. We would pose the question, okay, what's the direction of the force exerted by the planet on the satellite? And I was unable to get a really good answer. So we got into this discussion. And I ended up stating the law. Okay, of course, there's a vector statement of the law as well. And I kind of think I've got that one down here too. But two particle-like masses exert equal and opposite forces of attraction on one another. I'm not sure I even said equal and opposite. Yeah, I did. But it's sufficient to say that the forces of attraction act along the line segment joining the two masses. So if we have this line segment, which we've called the R vector, well, it's not a line segment anymore if it's a vector. You got the line segment. The R vector goes along the line segment. And gravitational force exerted on this mass is toward this one. The gravitational force exerted by this mass on this one is back toward this mass. Now, there was an objection raised. Well, how can the smaller mass exert as much force on this one as this one exerts on a smaller mass? Again, that's a very natural confusion because experience tells us that satellites orbit the Earth doesn't orbit the satellites. So it appears that a satellite has no effect on the Earth, and that's pretty much true because the Earth has such a great mass. You know, satellite orbiting the Earth has such a small mass compared to the Earth that you can't even detect the Earth's reaction to that satellite. But that doesn't mean the satellite isn't exerting a force on the Earth. And I use the example of the Earth and the Moon. The Moon is, I think, maybe 1/80th the mass of the Earth, somewhere around about 1/64th the volume, which I want to give it 1/64th the mass because they're similar composition. I'm not going to get into that. Maybe less iron at the core of the Moon, and I think that's actually it. So what happens is these two orbit a common point. Okay, it's like this. The Earth is actually in a small orbit around the Moon, just as the Moon is in a much bigger orbit around the Earth. And the point where the point that the Earth orbits is pretty close to the surface of the Earth. So in a month, the Earth does this little orbit about a point on its surface, or near its surface, and that's easy to calculate, very easy to calculate. So, you know, in the case of the Earth and the Moon has enough mass that you can actually detect the force it exerts on the Earth by the Earth's behavior, and of course it's easy to see the effect of the Earth's attraction to the Moon. Well, anyhow, there we have it. Now, the question was, show that the planet, the larger mass, can't exert a torque on the other. And actually neither exerts a torque on the other. And the reason for that is simply that in order to exert a torque, you have to have a component of the force that's perpendicular to the moment arm. And again, something we discussed. But maybe isn't really related to this situation. So we go back to the explanation of torque, which is pretty redundant with the explanations I gave earlier. If I've got a force here on something, think of some beam like the ones we've used in class, rotating about this axis, then clearly a force in this direction will tend to rotate the thing like so. And the force that actually causes the rotation is the component of this force perpendicular to the incline. So again, if we replace this force by its two components, we see we have the F perpendicular and the F parallel, perpendicular to the incline, parallel to the incline. We've got that little green line through here, so it means that we no longer have this, we just have these two. And we know that if we have an axis here, if we pull or push in the direction of the beam, it's not going to cause any rotation, only to push or pull in the direction perpendicular to the beam is going to cause a rotation. So the torque is going to be the moment arm, the R vector, the magnitude of the R vector. Well, the magnitude of the torque is going to be the length of the R vector, this distance here, times the magnitude of the force. Okay? So the magnitude of the torque is the magnitude of F times the magnitude of the R vector, F perpendicular times the magnitude of the R vector. And I've written that as F perpendicular dot R, it's a dot product. And then I wrote it as F perpendicular R. I guess I didn't write it as a dot product. But then I wrote it as F perpendicular times R. Of course, without the vector sign, these are just the magnitudes. So we want to be clear about that. Okay, so anyhow, that's the torque. A force perpendicular or parallel to this beam has no effect. Well, same here. There's no beam between here and here, but a force in this direction is not going to tend to cause rotation. And that's why the torque exerted by gravitational force between two particles or particle-like masses is not going to cause any, well, the torque is going to be zero. I lost track of my sentence. The gravitational force is not going to produce any torque. The torque is going to be zero. And this has profound effects for satellites, leads right to Kepler's laws, because if a satellite is orbiting like this, you know that the change in its angular momentum is the product of the torque and the time interval. And since there's no torque, there's no change in angular momentum. So, very important idea. Okay, now I went ahead and talked about this definition of the torque that we've talked about in class. It's cross product of R and F perpendicular, which is just a cross product of R and F because of the way the cross product works. And we worked that out down here. And then we talked about the right-hand rule. To get the direction of this torque, you put your fingers in the direction of the R vector so that you can turn the force toward the R vector. Well, if my fingers are like this and I turn my fingers, they don't go toward the R vector, they go this way. But if I have my hand like this, then I can turn the torque or the force vector toward the R vector. And now we see the direction of the torque out of the board. We had a longer discussion of that in class. So that's just how we do the direction of the force. So the R cross F perpendicular, or the R cross F, doesn't matter if I'm turning this thing toward, turning F toward R, or F perpendicular toward R. F is out here, F perpendicular is here, but in either case, the fingers have to move this way, giving us a torque out of the board. So that's the direction. R cross F, the cross product of two vectors, then has the direction that you get from the right-hand rule. It has a magnitude equal to the product of the magnitude of the two vectors times the sine of the angle between them. And this is the magnitude of R times magnitude of F perpendicular, because the magnitude of F times the sine of theta is the magnitude of F perpendicular. Okay? Because why? F perpendicular, if theta is the angle here between R and F, the sine of theta, well, you multiply the sine of theta by F, and you get the magnitude of F perpendicular. Multiply sine of theta by the magnitude of F, you get the magnitude of F perpendicular. So that's it, and that's a very important idea, especially if you want to talk about motion of objects in a gravitational field. So we summarize a lot of what we have here. The change in angular momentum is the net torque times the time interval. The work done by a net torque, of course, is the net torque multiplied by delta theta, where this is just the magnitude of the net torque. And actually, you got to be a little bit careful. You got to be a little bit careful. These are actually vector quantities, and this is actually a dot product. We haven't talked about the dot product, so I'm going to leave it a little bit imprecise right now. Now, you're supposed to know about the dot product, I haven't talked about it. It's actually the vector tau net by the vector delta theta. Right now, If tau net is in the direction of delta theta, then it's positive. If tau net's in the direction of opposite delta theta, then the work is going to be negative. Okay. And then we have accelerations, your net torque divided by I. Also, the change in L is, the L standing for angular momentum is defined to be the change in the angular momentum. The quantity I omega, moment of inertia times your angular velocity. And for constant I, this is I times delta omega, and these are really important relationships that we talked about in the context of the rotating systems we've been looking at. Net force versus X. We have a graph of net force versus X for linear restoring force. Okay, now this, of course, is clear from the context of what we were discussing in class. Okay, here's a linear restoring force. F net equals negative kx. That's a force exerted by an ideal spring. And when x is positive, and of course, I don't really want to write it down. This is the net force relative to the equilibrium position, relative to the x equals 0 position, which is the equilibrium position for the spring. So we have F net equals negative kx. That's for an ideal spring. And just wanted to contrast this with the rubber band. The force exerted by a rubber band with respect to, as you stretch it, is going to be like this. Okay, now it doesn't actually do this because the rubber band can't exert a compressive force, but if you have a mass already stretching the rubber band a little bit, which is the case of this kind of models, your result is going to look like this. Okay, the rubber band stiffens a bit, and you get this sort of thing as you move further away. The point being, and we've studied the rubber band, we've got data for force versus length, and hopefully we've graphed and analyzed it. The point is that close to equilibrium, this linear model stays fairly close to the force curve for the rubber band. Now, I've kind of exaggerated the curvature of this thing. It doesn't have that much curvature, at least till you get out near the breaking strength, but it acts something like this. So that when we suspend a mass from a rubber band, the simple harmonic motion, well, we don't actually have simple harmonic motion. That only occurs if we have a linear net